Good afternoon, everyone. Public speaking, the most terrifying thing you can do. But my name is Mukul Sabharwal, and I work at Microsoft on the Bing.com front-end team. A little bit about my team. My team is responsible for the front-end stack server performance and utilization. And we also try to understand and improve the application of the performance of the application. We're also the developer platform team, so we do things like compiler upgrades, static analysis tooling, providing developers with and engineers with tools that they can use to understand the code base, like DSLs for making front-end stack development easier. So we're pretty much at the lower end of the stack development from a developer's perspective. Just want to give an overview of what I'll be talking about. We'll quickly go over Bing.com front-end, what I mean by that. I mean, you all know it's a search engine, but just wanted to give sort of context. And then what is profiling in production, why we would profile in production, and how Bing.com got here. Then I'll introduce BPerf, the production and profiling tool that we use in Bing, and walk you through it, and then talk about a case study we did with it, and then talk about what's next for BPerf. We'll cover where potentially audience members can use it. So the Bing.com front-end stack is a C# ASP.NET MVC application, runs on .NET, deployed to Windows Server 2016. And it is the entry point for all traffic for Bing after an Azure CDN. So we're pretty much, when you go to Bing.com, you're typing a search result, or when you go from your browser to a search result. And we're basically rendering the rendering layer, so we take the DSL that we have, which is called Razor. It's an open source ASP.NET DSL that will then convert it to HTML. So that's obviously oversimplifying it, but for the context of the talk, I think that's relevant. And then I'm not going to talk about our backend, which is the complicated sort of fetching things from the indices and showing that on Bing.com. It's for the purposes of this talk, it'll just be a set of microservices. We get Microsoft Bond, which is like Apache Thrift, from that, and then we render that as HTML. So up here I have 3 pictures of what a Bing.com search result looks like. And what I'm trying to show here is that for Bing.com, there's a lot of things that are impacted by the data. So on the left side, we have Olympics 2016, which is pictures, player stats, a lot of information about the score tally, and then it's a pretty rich page. There's the next query, which is Katy Perry. It's also a rich page, a little less multimedia, but still quite a bit. And there's a few information about the about Katy Perry. And then on the far right, we have a typical sort of medium tail query, which is something like core CLR, where the intent is you want to go to the first link, and the information is pretty textual. We have some related searches on the right, but it's a fairly plain vanilla page. So this is to sort of showcase that while we are a single shared code base, this kind of data can dominate how our application response times are. I'm sure many applications are like that, so I wanted to put that there. And then just a little bit about developer agility. We do full production releases multiple times a day. We have about 100 changes, 100 commits coming into the branch, and lots of A/B experimentation. Pretty much everything that happens in Bing runs through A/B experimentation. So the combinatorial explosion of all different pieces of code that are running is pretty enormous. So essentially, there's no canonical workload. You're not looking at a single, the Bing.com frontend can't just be a single canonical workload. So what is profiling in production? Succinctly, it's basically the capability to identify and isolate lines or regions of code that have unusual application behavior. They could be highly latent requests, or they're taking down your machines, but basically something unusual. It could be directly related to developer code check-in, or it could be an indirect consequence of a library call that you're making, or an operating system call that you thought was previously too infrequent, but it is now more frequent. And another sort of tenet of profiling in production is that the profilee, the thing that you're trying to get data about, you shouldn't perturb its performance. So you shouldn't. It's not like running a debugger and then you're actually tanking the performance of the application. And then often, profiling in production ends up being platform specific. So for Windows, there's event tracing for Windows, and Linux has perf, and there's also dtrace, which is a very popular tool for such kind of instrumentation. But what I want to get to next is that this isn't a replacement for higher level tools. Higher level tools are critical still to an SRE's toolkit. So just to sort of drill down, what do I mean by these high level, low level tools? The high level tools would be things like the aggregate performance counters that you have, which are requests per second, latency of a request, business metrics like successful searches conducted per second or orders received, et cetera. And then slightly lower is for each of these aggregate counters, you could have dimensions. Is it coming from a specific country? Is it a particular browser? And then further down, there's these code markers, effectively developer instrumented regions of code where you have a start and you have a definitive start and stop that you'd like to trace for utilization, memory, performance, or just wall clock time. And then further down is where we have CPU profiling and memory profiling, effectively allowing you to get information about the application's runtime characteristics, either from a CPU perspective or a memory perspective. And then even further down, this is something that's sort of been a new avenue, which is code recompilation for telemetry. Essentially, you have your code is running, but you'd like to make changes to it to actually understand more information about it. So I like to think of it as high level helps you identify things and potentially mitigate, and then low level tools help you understand. So why would one profile in production? Why did we start profiling in production? So high level tools are essential and critical at identifying problems. You can't have profiling in production but not understand that you have a 20% failure rate for your requests. So certain things like latency of operations and successful RPS, these things are absolutely critical. They're the first level of defense. They're also very good at mitigating things because now you can fail away traffic from a particular data center, or you can turn off a feature in production. These things can't go away. But what production profiling is useful for is in some cases when mitigation is not an option. What if you have a user query or input that's triggered failures and you don't have it behind a feature flag? And now you've identified a problem, you don't have a mitigation, but you need understanding. So performance and production tools basically help you get deep understanding of the application without necessarily having to attach a debugger or run a debugger on your production machines. That doesn't mean that a debugger can't be made production safe, but usually people don't do that. And then often you can get root cause analysis at the incident time because of profiling in production. So given the fact that we have agility for all the code that we ship, one of my colleagues recently told me that we're not paid for the 99.99% of the times when the application is working. It's for the 0.001% when it isn't. And if your response to the incident is, well, I don't have the understanding, then that's what we're trying to sort of push the bar with here, is that understanding the problem should be part of the SRE toolkit. So like all incidents in all our universes, Bing.com had an incident at 3 a.m. They all started at 3 a.m. I'm not sure why. And this one was 4 years ago, and basically there was a user query that triggered a feature that didn't have a feature flag, and this piece of code, which we would identify later, was going into a non-obvious infinite loop. We actually didn't know there was an infinite loop. All we saw was there was a query coming in that it never finished. It would just be there in the system. We wouldn't see it. The only way we were able to even understand it was we were binary searching through the log entries. We were saying, okay, the request start has been logged, but somewhere in the middle, there's this operation log that is usually there. It's not there. And so 5 or 6 developers at 3 a.m. are now searching the code base. So The problem was, once this query is in your system, there's a CPU core unavailable from our perspective for an indefinite amount of time. So the challenge here was, how can we get to the bottom of this? And so this piece of code had a non-obvious infinite loop. It had multiple control variables. You couldn't look at it and say, okay, this has, you couldn't go to the developer and say, hey, why is this in an infinite loop? And what this code was trying to do was, it was trying to, you can imagine Bing has, you have to place things on the page, and it was trying to find rectangular spots on the page and then placing them. And so starting from the right side of the page and then moving up and trying to do that, and then it would never terminate. Obviously, there were check-in tests, there was continuous delivery for it, but there was a condition that wasn't caught. And the biggest problem was finding the code. Like, how do you find an infinite loop running inside your application? So that was a big challenge. That, unfortunately, we had to use humans to binary search through it to get to that. And then the second problem arose, which is the developer who checked in the code didn't have any idea why it's in an infinite loop. So now you're thinking, wait, how do I debug this? So we actually had to make a standalone app, get the code there, and then debug it to find why there could be an infinite loop. There were other ways we could have done it, but that's what we ended up doing. So that was pretty exciting. So what would have been great at this point of time, right, at 3 a.m. 4 years ago? At least one thing would have, let's look at the finding part. A CPU profile of the application, or just a CPU profile of the running request thread, would have told us what's hot on the CPU. So we'd at least know the function to go look at its history, git blame it, etc. But it doesn't stop there. Once you've found it, it probably took us about a few hours to find it. Then you need to know what's going on here. How do you understand this piece of code? And if somebody had told me you can inspect local variables or look at parameters, that would have been essential, because we would have said, oh, this is an infinite loop. Here are the loop variants, and we could have concluded a way to solve the problem. But we didn't have it then. So what we have now is BPerf. What BPerf is a always-on CPU, at the core of it, an always-on CPU sampling profiler. The profiler itself is based on event tracing for Windows, which in Linux and BSD parlance is either based on perf or dtrace, and is able to collect call stacks at these event points. So for any event that is emitted, there's the capability to have the Windows kernel, in this case, capture a call stack. And what we do is we basically run this CPU sampling profiler all the time on all machines on our front-end stack. We also have periodically triggered memory sampling profiler. Memory sampling is a bit trickier because often there will be, if you're doing a lot of native code development, there's often different allocators. They'll hide the actual intent of the code. The developer may have said, oh, I'd like to make a string array, but it might be hidden from a larger pool of memory, and therefore it's difficult to get to it. So you need to be more invasive, which means it's more expensive to run it on production all the time. So we don't actually run it all the time, but we run it every 5 minutes for about 30 seconds. So it does affect the 99th percentile latency, but most users, 95th to 99th isn't impacted. We also collect the disk I/O information, so you've accessed a file, read it, or written into it, and also network I/O information, so TCP or UDP connections, TCP connections that you may have opened, or UDP datagrams that you're sending. And then very critical to Bing.com is .NET information. So because we run on .NET for multiple reasons, including security, the fact that we take user input from customers, and then we might sometimes display that user information as search history. So running on .NET gives us security and also developer productivity. So having .NET information like exceptions that were thrown on the request, if a garbage collection was triggered, or was this request also be impacted by JIT? These are important things that we look at. So again, this kind of analysis is practical only when high-level analysis points to code. And oftentimes, you at least have It doesn't have to be a single machine, but you've isolated it to a set of machines, and you can look at this machine in isolation at a specific time interval. This is the most common use case of BPerf we have in the code. And the hope is that you've found the offending code in action. And this is, we didn't used to always run the profiler on 24/7, and then we realized we were missing many cases where things were not caught in action. And so this is a sort of a simple view. I don't have network connectivity, otherwise I would have shown you. This is what essentially an engineer does. He basically identifies the data center, which is on the left side, and the machine name, and he has identified in this case in 2016 of August that between this and start time and end time, they're trying to look at either a memory, CPU, or exception profile. We also track contention. That means every time there's a lock that's in the code that's contended, that's also logged and available. So a little bit more about the sampling profiler. When I spoke about this internally at Microsoft, there was a lot of people who were like, "You're running a profiler on production all the time?" Wait, there has to be a severe latency impact. And the default settings for profilers like perf on Linux and ETW on Windows, there is a significant impact. It basically pauses all logical cores for every millisecond and then walks a stack. And on Windows, walking stack on 64-bit code is a bit more expensive than 32-bit code. So there's a lot of nuances. So definitely doing it on the default settings is impactful to production. But what we do is, given the scale of Bing, we basically take an order of magnitude reduction in sample rate, so we only do it every 10 milliseconds, and that gives us a pretty good statistical profile without really impacting production at the 95th to 99th percentile. So pretty much every 10 milliseconds, we still do pause all running threads, but it's only for about 100 microseconds, which is not noticeable. And then we correlate this with either a background operation that may be going on or a search request. So when an engineer wants to drill down to a particular Bing search request and understand that specific request, we have the data for that. And then we can filter out things like other logging that you may be doing, some periodic tasks that are running in the background. We also aggregate at the data center level. So the data center aggregation is very different than the one that I just showed you with that snippet of a view. The data center aggregation helps get things like utilization. How much time am I spending in string compare? On Windows, we have UTF, I don't want to be specific, but we have double byte characters and single byte characters, and a lot of time is spent converting between double byte and single byte, UTF-16 to UTF-8. So these kinds of things are not noticeable in a single machine profile, but when you look at it at a data center, when you have 10,000 machines in your fleet and you're seeing that 2% of your CPU across all these machines is doing UTF-16 to UTF-8 conversion, you start looking at that problem in a different way. So that's the utilization side of things that this helps. And then finally, the last thing that we do on the machine is, since we're managed code, there's jitting involved. The actual code that developers write get placed in memory and then jittered in memory at different locations. So we actually have to do a step called canonicalization, which is we take the addresses that we see from the profiling tools, and then we canonicalize that to like a name that is something that will be across the entire fleet that's independent of where the code was placed in memory. So a little bit about our periodic memory sampler. As I said, memory sampling is a bit hard. So for managed memory, what we do is every 100 kilobytes that somebody does a new object, they make a new string or they make a dictionary, every 100 kilobytes we take a sample and collect its call stack. This is pretty coarse because you can imagine there could be a guy who could come in and do 99 kilobytes of allocations, and then the poor person who did 1 kilobyte gets attributed and said, hey, you just made a 100 kilobyte allocation. So it's not as fine-grained as CPU, but it definitely, we don't actually have cases where there's a guy who doing 99 kilobytes and then one person doing 1. So it works out. And then call stacks are acquired and handled similarly to CPU samples. We also added disk and network profiling in BPerf, primarily because if you're in a shared code base, you have many developers writing code. We do have static analysis checks that'll say, hey, don't write to a file. But sometimes they're needed, and it's difficult to be able to let static analysis tools go in and basically get all your code run through. So what we do is we can actually profile at runtime, and at runtime it allows you to basically get information about which file you accessed, which sectors of the file we're accessing. And at runtime, we basically disallow that. So we'll flag it, put it in a whitelist. And network I/O, we do the same thing. So you can imagine if you have a set of microservices or you have these applications talking to each other, if everyone is making their own network connection and they don't have a single place where you can instrument all network outgoing calls, it becomes difficult to manage that. And so we added this instrumentation so that despite people using our library or they don't, we can still get access to the network information. And then I was talking about the .NET information. Basically, we collect garbage collection. So a lot of times what will happen is that there'll be a request, like Katy Perry. Let's say it takes 50 milliseconds on the front end stack. But suddenly it'll take 100 milliseconds. And there'll be all these alerts that'll wake up. And what happens is that maybe this request got impacted by something like garbage collection. And so we add that information in the request log that's saying that, hey, this request got impacted by garbage collection. So when an SRE or even an automated tool is looking at it, they can exclude these requests. Same thing we do the same thing for exceptions and JIT compilation events. Exceptions, we have a global rate that makes sure all the call stacks are correlated. And then we also are able to identify cases where a developer has purposely swallowed the exception. So you can try catch, and then you can actually, we still get to see those. The final step here is the code. The final step of the low-level stack here that I was talking about is the code recompilation. This is the most exciting avenue for BPerf. This is the sort of the epitome of being able to get low-level instrumentation to help SREs. So what we have is the capability to modify code running in production. So at a method level, if you have methods that are executing code, we can actually change the code at runtime, annotate the local variables or annotate the parameters, and give information to an engineer who might be investigating a live site incident. We can also add try catches. So sometimes, in fact, a lot of times, there's a null reference exception, and most of the time all you have to do is take the code, and if you were to put a try catch, you can at least mitigate the incident. So low-level tools actually help you mitigate incidents. This would have been a production redeployment previously. And so an upcoming case for us is this notion where the fact that we can recompile methods online, we do have the capability to optimize them at a higher level when we see them being executed quite often. So that's a step that we're sort of getting into. And then I wanted to talk about data center aggregation. Unfortunately, I'm going to skip a few slides just to give you a view of what it looks like when an engineer actually gets to it. So this is the view that you saw already. These SRE, as a high-level tool, has identified the problem at the time period. This is a sample machine that has something going on. Okay, I think you can see it. And this is a summary view of what the CPU was doing at this time. And so you're seeing, okay, we're doing some deflate. This is some internal code that we're doing, and from this view, he can actually, what's not visible is that you can click this, and I'll show you the next view here, and you can actually see the call stack. So it can tell you who's doing the unzip operation. In this case, this is fairly benign. This is something we do all the time, but you can actually see this, and the source line is the sort of killer feature here. You can actually click the source line, and it takes you to the line of code that is actually doing that operation. This is the same thing for memory. You can see a byte array being allocated by this LZ4, again, compression. And this is the view that an SRE will see when he clicks the line of source code. So he actually sees the line that was causing the issue. So my final case study here is the unknown gap that we have. So this is like the Chrome trace viewer, but you can host it in a web page. So we have this, and there's an unknown gap here. And basically, this is a highly latent request. The instrumentation doesn't tell you, but this is the function signature. The function is called decrypt. It takes a byte array, returns a byte array, and the issue here is that it was actually making a network call. And the network call was basically there behind the decrypt function, which is pretty unusual. So in conclusion, I just wanted to say that high-level tools are great at operating on aggregate metrics and critical in the SRE toolkits, but I want to encourage people to have production profiling tools in their toolkits. You can try BPerf if you're on Windows. We are taking BPerf to the next level with Linux on perf, but there's also Brendan Gregg's tutorials which work on perf and Linux, so you should be able to see that. That's all I have.